actually have direction. They don't really have clearly defined directions to them. You see, when we use the Suvat equations, so if I write one of them, for example, S is equal to ut plus half at squared, right? When we use this equation, we're just subbing in values. But one thing that we shouldn't forget is, well, displacement is a vector, u is a vector, a is a vector. Remember, time is a scalar. Time doesn't have direction. So these are actually vector quantities. And so where am I going with this? Well, because these are vector quantities, when we use numbers, when we use scalars, we don't just have to use scalar quantities. We can actually use proper vector quantities. So what we can do instead is we can use the same Suvat equations, but instead of having them equal to, numbers, we can actually have them equal to scalars. So I'll give you an example so this makes more sense. So you could have it equal to a vector 1, 2. You could have u equal to a vector 0, 0. You could have v equal to v equal to 1, 2, and then say we don't know a. Then we would have t, I don't know, is equal to, say we don't know that. We can use the same Suvat equations, is my point. So say if I wanted to find, how do you call it, a, for example, well, you would just use v squared is equal to u squared plus 2as. So you can use the same equations. Actually, no, let me try and use it. Let me actually think about it. Okay, let me say time is like 6 seconds or something. So let's say time is 6. So one of the equations that you can use is v is equal to u plus at, right? Yeah. So then what I can do is to find out a is I can just, do v minus u divided by t. So then I can work out what a is. So v would be equal to 1, 2 minus 0, 0, all divided by 6. So then you would just have a 6 of 1, 2. So then you would just have a 6, 2, 6, or just a third. So, yeah. Do you understand that? Yeah. Now, why am I showing you this? This is what Chapter 8 is about. So Chapter 8 is about basically dealing with kinematics, or basically displacement, velocity, and acceleration, but with them as vectors, because we've just used numbers to them, we've just assigned numbers to them the whole time, right? So first shift, for example, in projectiles, we just say displacement's 9, velocity's 9, acceleration is 2. But what if we actually had two directions or two-dimensional situations similar to projectiles? How would you model that scenario? So that's what Chapter 8 is about. It's there for you to appreciate that displacements, velocities, accelerations, they don't just always have to be equal to numbers. They can actually be equal to vectors. So that is the theme of Chapter 8. Pretty much. That's it. You happy with that? Okay. That's great. And one thing when you do Chapter 8 is actually drawing out diagrams, and I think drawing out diagrams definitely helps, but that's just something that's, I guess, a given mechanics. Okay. So 8.1 is a bit of an interesting one. It's not exactly clearly written from what I can make out. So what are they saying here? If a particle starts from a point with the position r0, moves with the constant velocity, then so pretty much what they're telling you here is they're basically just saying, well, if you have S is equal to UT plus half AT squared, where we know S is a vector, U is a vector, A is a vector. Because it's constant velocity, say if you equate this, because it's constant velocity, we know acceleration is 0. So we can just get rid of this. So now we're just left with S is equal to UT, like this. So really, all right, V for velocity. What they've done is whenever you see R or the position vector R, it's pretty much the same thing as S, because displacement and position, they're very similar, right? They're pretty much the same, yeah. You know what? The only difference is you could actually argue that displacement is basically, you could argue it's R minus R naught in this case. And I'll explain where this comes from in a second. But actually, let's talk about it now. So where does this actually come from? So what does displacement measure? Well, say if I give you an origin or basically a starting point, right? And if I said, okay, well, we have a particle. We have some particle. And I want to measure the displacement. Yeah. So that would be your vector S, right? Well, actually, let me make this a bit more clear. How am I going to explain this, actually? Okay, let me do this again. Yeah, suppose I have an xy coordinate or Cartesian coordinates. And, okay, so I know that this is the origin. Yeah, and say we have some particle, say here. But say if I want to measure the displacement from not the origin, but like some other point. Let's say I want to measure the displacement from some point A. So let's say A is here. So I want to know what is the displacement of this particle from this, like this position A. Okay, so basically what's happening is, well, you can basically use vector addition or the triangle law. You can kind of appreciate, okay, so you would have some vector O to A here, and you would have some vector, like, yeah, you would have some other vector here. So let me actually call this point here B. So this is your starting vector. So say A is like your starting position, right, for this ball. And this ball was starting here and it's ended here at B. So the ball starts at A, but then it ends at B, right? It does say it doesn't start at the origin. So pretty much you see this R naught term here. So this R naught term is basically, it exists in case if the position of an object is not at the origin. So say if your starting position is not at the origin, right, you would have this R naught term. It's like a correction term. So if this didn't exist, then you're starting at the origin. But because it's here, it implies that you could be starting anywhere from the origin. Pretty much. But I'll just prove this to you anyways. It's not important, but I guess it will help you grasp good intuition towards it. So S, you can actually just say, well, if this is R naught, I can say that this is some position vector R. So I can say R is equal to S plus R naught. So if I add this vector R naught and this vector S, I'll get R. So then you can clearly see, you can just rearrange this expression to get the displacement. Right? Do you remember how I said, like, displacement? It's you basically define where you start from. There's no right or wrong. So I can, Yeah, so remember when we were doing some of the Suvac questions in the past, where they can throw a ball, right? So they can throw a ball from a height. Well, actually, remember what I said. You can define your starting displacement here, or you can define it here. So you could define displacement is equal to 0 from the ground or from when you throw it. Do you remember I said that? Yeah. So that's the whole point. So because that's a one-dimensional problem, it's quite straightforward. But here, if you're dealing with multiple dimensions, how do you visualize that? Or just assume, I could say, um, I could basically move this axis however I want. Sure. Um, that might be a bit complicated, but okay. But does that make sense, generally speaking? What I'm saying that with where this formula comes from for the time being, you're happy with that? Yeah. It's not really too important. Don't worry about it too much. But generally speaking, I think this section is not nice. It's not nice in the sense that I don't like the explanations they give. I think it's best to start from what you learned from in calculus. So another way of deriving this is actually a very nice way. If you cast your mind back to chapter 11 of static mechanics, so the variable acceleration stuff. So remember there was a couple of relationships that you've learned about. So you must have come across V is equal to ds over dt, and then acceleration is equal to dv over dt, right? So you've come across these two. Now remember, based from what I was just showing you earlier, you can apply the exact same scenarios for when these two things are vectors. So what's quite interesting is um, actually it won't make much of a difference. I'll do it anyways. Why not? If you think back to separation of variables, some you've done a couple of weeks ago. If I was to bring, well, which one should we start with? We could start with either one. Which one's probably the most sensible? Let's start with the left-hand side. So then if I bring dt next to the ds and then integrate both sides, right? Notice what would end up happening here is you would just get v t, right, is equal to s. But then there's a couple of things that will raise some questions, right? Which is this formula doesn't look completely correct. And why is that? We haven't defined limits for this integral. Now, is it important? Yeah, you could argue it's quite important. So remember what the top and the bottom of the integrals tell you. So they tell you, they tell you a top and a bottom, all right? A start and an end. So what's really important is that this tells you the ending position, and this will tell you the starting position, or starting time, ending time. Usually, we always say the starting time is 0, and then the ending time is just t. Same here. You see with ds, right? And this is really, really important. We say that the ending position is r. The starting position doesn't have to be 0. It could be anywhere. It could be r0. For example, if you're talking about a lighthouse and a ship, right? Say here, say if there was a lighthouse in the center of this grid. So if I said there was a lighthouse here, and if there was a ship, look at the ship's position. It's not at the origin, is it? It's somewhere where. So wherever this position is, we say it's R0, because a ship doesn't have to be at the same position as a lighthouse. So sometimes it's very, very wrong to set the starting displacement to be 0, 0, or 0, right? It's very inappropriate sometimes. So that's why we say R naught instead of R. Or sorry, R naught instead of 0. So if you were to actually do this with the limits, then you would get something that makes a bit more sense. So if I sub in t0, it doesn't make a difference. You would just get vt. But look what's going to happen here. Well, you would have r minus r naught. You see my point? So that's another way of deriving the expression that they've, how do you call it? They've requested. 1 second. Yeah, you don't need to worry about how I've derived it. It's just from the. They usually won't ask proof or anything like this. But yeah. That's just so you understand where the formula comes from. This isn't really too important. But yeah, do you have any questions on this? Realistically, a nice way of doing these problems is actually visualizing it on a diagram. So I usually don't recommend using formulas like this for now. Having a good diagram is very, very good, which just as simple. So what I'll do is I'll go for example 1. Okay, so it says a particle starts from a point with a position vector 3i plus 7j meters and moves with a constant velocity of 2i minus j. You know what's really, really important is if you draw the diagram, you'll start to realize you probably don't even need to use the formula that they give you. So if I say that this is my origin, so 3, 7 is somewhere here, for example. So that's a starting position. And we know that the velocity will be 2 minus 1. So 2i minus j. So it might be something like this. Just give me a second. So the position is 3, 7. All right, does that make sense, what I've done there? Just do that a bit bigger. Okay. Let me just make this a bit more clear. Okay, let me say that 3, 7. So I'll just illustrate why you don't need a formula. Okay, and it says what does it say here? So it says find the position vector of the particle 4 seconds later. So this is just a simple speed is equal to distance divided by time. Notice what they've done is they've actually just used the they've just used this formula. Okay, yes, they're using this formula, but really they're using this formula because this term will just completely disappear, right? So you would just be left with S is equal to UT. But what is this actually telling me? Well, it's telling me how far I've moved. So if you look at S here, well, the displacement that's going to be moved in that time just be 2 minus 1 multiplied by 4 seconds, right? So that will be 8 minus 4. Okay, so because that's 8 minus 4, I know within 4 seconds what's going to happen is, so that's 1 second, 2 seconds, 3 seconds, 4 seconds. So it will be somewhere here. So what's happened here is, I know the particle's moved down some point. So what do I have to do to find the final position? You're just adding it. You're just adding this position moved or the units moved to what they've given me here, and that's it. Yeah. So you can use the formula, but I don't really recommend it. Because if you just draw a diagram and just kind of use some intuition, you'll arrive at the correct answer. So that's 8 plus 3, which is 11, minus 4 plus 7, which is 3. Does that make sense? Using the formula is quicker, but I really don't recommend it. Really don't. Okay. Part B, find the time at which the particle is due east of the origin. Give me a second here. I don't know if I'm misinterpreting this. Due east. Oh, okay, right. So basically what they're asking for is, okay, so this is north, and then this is east. So when it says east of the origin, I'm guessing it's when the particle is intersecting the axis. So basically, whenever the y position is 0, basically, does that make sense? So when the y position is 0, then we know that we're on east. Does that make sense? Yeah. So that's what they've done there. So how have they done that? Well, you basically let the time be t. So if you were to use the same equation, s is equal to ut plus half at squared, that goes to 0. So then the displacement that will be moved within some time t seconds will be 2t minus t, right? Yeah. And then what we're doing is we're just adding that. We're doing the same procedure again. So we're doing 2t minus t, and we're adding that to the the original position. So that was 3, 7, right? So then you would have 2t plus 3, and then you would have 7 minus t. And then remembering that because it has to be due east, the y value has to be 0. So what they've done is they've just equated this to being 0. So t is just 7. Does that make sense? I think the wording for that question is a bit poor. Yeah, there's better ways of wording it. That did confuse me for a bit. But yeah, okay, this is much better. This is a lot better. Okay, now if you look at the second point they give you, this is important. Now, what's a beauty in this, and this is why I don't say chapter 8 is really difficult. I say it's actually one of the easier chapters. It's not hard to memorize something like this because you've seen it before. You just have to put in your mind that this could also be in the form of you can use these formulas with vectors. That's the new thing here. That's it. I'll do example 2 and example 3 a bit quicker now. So example 2, it says a particle P has a velocity minus 3i plus j at times t is equal to 0. So they don't give us a starting position. It says the particle moves with a constant acceleration 2, 3. Find the speed of the particle and the bearing at which. You know what? You can have a go at this. Do you have an idea of what to do? So could you use the formulas here? So have a go at this example because I think you might be able to do it, and then you'll realize it's not as bad as you think. What did you get? Yeah. Yeah, good. Well done. And then the speed? Yeah, or 10.4. And then what did you get for the bearing? Not 12.9. So I've actually done quite a nice diagram for this. I'll just show you. Well, sort of. So one thing that would definitely help is draw out how 3i plus 10j looks. And remember what the rules for bearings are, right? So remember what the rules for bearings. Well, you always have to measure them from north, right? And then the other thing is always measure them in a clockwise direction. Okay, and that's it, really. And then, of course, if it's two digits, just put a zero on the front of it. That's the other thing. So north and clockwise. So that's why they're measuring this angle here. And that's why they did tan theta of, that's 3/10. Realistically, what's more important is, let me just redraw the diagram out here. So draw out what the velocity vector looks like. So then we know that's 3 and 10. If you did theta here, that's okay. That's not a problem. So what you can also do is you can just say, oh, well, theta is just tan inverse of 10/3, right? And then what you should get is you should get something that's roughly, what would that be? 73.3-ish, I think. And then if you get this to be 73.3, then you can just find out that the bearing, or this angle here, would just be 16.7. So then therefore the bearing will be 17 degrees. Does that make sense? That's basically the way you should approach that. Okay, do you have any questions? It looks like you always rounded to the nearest integer, yeah. Okay. You know what? Okay, so have a go at this question, and this is a very typical exam question. This is a good one. So have a go at A and B. Let me know what you got. This question's quite challenging, but you'll learn a lot. So just have a go at A and B for now. So just A and B. How are you going on? Okay. Okay, great. What did you get for A? Hmm? That's really good. Well done. And then for part B, it's a bit of a long expression. Yeah, that's correct. Good. And then you got. Hmm. So just repeat that last bit again. Yeah. Yeah. Okay, right. Yeah, that's correct as well. Okay. Now, for part C, this one's very tricky. Um, I'll give you a bit of a hint for it. When it says they're directly northeast of O, okay, so you don't know, of course, you don't know what the time, at what time that will happen. But what they're referring to is they're referring to the displacement vector. So the displacement vector at this time has to be oriented at 45 degrees, basically. When I say 45 degrees, you're probably thinking, where's the 45 coming from? Well, if you were to draw out the vector, actually, let me do this properly. Say if this is the ice skate array. Alright, I for ice skater. Yeah, and say if this is the fixed point O, right? Yeah. So if you imagine drawing a north from this point, if you were to imagine a displacement vector, that's northeast. So northeast, so that's east. Notice that's 45 degrees. You see what I'm saying there? Yeah. So have a think about how you might approach that one, and I'll give you a hint. Try and use your answer to part B to help you. I'll give you around 3 or 4 minutes. And if you're still stuck, then I'll help you. It's a good question, this. Just part C, yeah. It's very difficult. All right, do you have any ideas? Okay, that's good. Okay, keep going. Um, if you have an idea, then that's really good. Do you have any ideas? Hmm. Okay, I'll give you a hint. Um, so okay, nice try. It's 10. Okay, it's actually a very tricky question. So remember what the diagram I was showing you here to be, right? So if you look at the displacement vector, we don't know what it is, but we know one thing for sure. It has to be at 45 degrees, right? 100% it has to be at 45. So why is that so useful? Well, if you imagine constructing a right angle triangle properly, um, if you consider so you consider constructing a right angle triangle, we know one thing about the displacement vector. So it has to be 45 degrees. So the horizontal component for the displacement vector, um, that was 2.4 t minus 0.2 t squared, right? And then this component was 0.1 t squared minus 0.6 t, right? Yeah. Now, because this is 45 degrees, it has to be 45 degrees. Remember, tan of an angle is equal to the opposite all over the adjacent, right? So what we can do here is we can just say, well, tan of 45, well, we want the angle to be 45, right? Theta can be anything. But because we want it to be northeast, it has to be 45 degrees. Okay. So tan of 45 will be equal to the opposite, which will be 0.1 t squared minus 0.6 t, all divided by 2.4 t minus 0.2 t squared. So then tan of 45 is just 1. So notice you would just get 0.1 t squared minus 0.6 t is equal to 2.4 t minus 0.2 t squared. Now, when you solve this equation, you should get t is equal to 10. Did you try and solve the equation? This equation I have here. Did you get anywhere close to that? Or anything similar to? That's okay. But do you understand what I've done? It's a very tricky question. Very tricky. Do you want to have a go at part D? Okay. So fortunately, part D, it's not as bad as part C. Part C is the most difficult, but yeah, what you might not know how to do part D, but it's not as bad when I show it to you. Do you have any ideas how to do part D? Mhm. So this is a good question. If I was to show you when they meet, what would you notice if they were to meet? So if I said, okay, go ahead. What vector though? What would be the same? Yes, you're very close. Yes, so they would have the exact same displacement vector. So notice what they've given you is they've given you the displacement vector here, and then you have the displacement vector from part B. So what would you do to those two? Exactly, you would equate them. Um, and then you'll notice something when you try and solve the equations. You have an answer? You stuck? Okay, so it's not as bad as you think. So if you look at the two position vectors, so if I say RA, or actually I don't like, I have to use R. So RA is the position vector for, what do you call it? The first scalar. So that will be 2.4t minus 0.2t squared. And then you have 0.1t squared minus 0.6t. And then you have the position vector for the other scalar, who we just know to be so 0 and then 1.1t minus 6, like that. So you equated both of them, right? And then what would you notice? You would notice that if you were to equate the I components, so you'd have 2.4t minus 0.2t squared, you can solve this. And you'll get an answer of, sorry, that'll just be 2.4. So t would just be equal to 12 here, right? And then if you were to do the same thing here, so you would have 0.1t squared. What would end up happening? You would also get basically like the same. You should also get the same answer, basically. You should get 12 as well. Let me just do that very quickly. That's a bit nasty, actually. You get a quadratic, right? From the looks of it, you would get a quadratic. It's painful. 17. Let me just double check that's correct. Second. (0.1t squared). Interesting. Huh. Could you just solve that very quickly? (0.1t). That should give you 12. I have a feeling that just doesn't give you 12. Mm-hmm. Oh, yeah, wow. I'm just shocked something like that would give you 12. For some reason, that just doesn't. Shocked. Okay, but anyways, yeah, you'll get 12 from that. Yeah, that's it, I guess. That is it. Okay, and basically the whole point here is, can you see how both of them yield the same values, right? So when I've done this, I've got 12. When I've done this, I got 12. Because the two times agree, they will meet. Suppose this one gave me a time of 5 or something, and the other one gave me a time of 12. Imagine there was no overlap when I was looking at both components, then they wouldn't meet. Do you understand? There has to be an agreement in both components in order for that to work. Okay. I think we'll call it there. So are you happy with this, what we've done? Now, this is actually really, really important. The last example especially, because what they do in the exam is they actually put 2 questions on chapter 8, from what I've seen. So yeah. So what I want you to do for homework is I want you to do question 4, 5, 6. Yeah, I think just do those 3. Or actually, maybe do question 9 as well. Actually, let me just see if there's any more questions like that. You know what? Scrap that. So 4, 5, and then yes, this is very good. This is very, very, very good. And then question 12 and 13. These are the type of exam questions you want to be targeting. 12 and 13. This will come up in your exam. Yeah, these are really, really good questions. And that after that, yeah, it's pretty much we're nearly pretty much done. I'd say that's if you actually look at the chapter, it's a small part of chapter 8, but realistically, the rest of it will go a lot more easier. I would say should be a lot more easier. All right. Do you have any questions? All right. If you don't have any questions, then I'll see you on Saturday. All right. No worries. Take care. Bye.